So last week we were affected by the typhoon. So many changes to the lecture. Today we are right here. So let's check on what happened last time. We don't have exam 2 anymore. So the exam score should be changed. It has been changed to homework. But it's a bigger homework, is it? Did you do the homework last week? No one replied. Did you do the homework? You didn't do the homework? Oh, so when is the deadline? Tomorrow? Today? Okay. Did you do the homework? Okay. Then please, can I see? Okay. So basically a shift and also more circle and then the failure model, right? Using the 3 models. Okay, thank you. Okay, you guys can hand in later on. So it's a bigger homework. So I think we should change the exam score. Not yet. No more exam 2, but it's becoming a big homework. So I think I can say it's a 5 point here. Let's see. So we will be missing 5 points. And last time there's no attendance. Right? Last week no attendance. Okay. So last time we assigned special homework 2. So basically, last time I asked you to do this, and you hand in today. And so far, if I give you 6 points, that's not enough. Maybe I increase the project a little bit. So this is for proposal. So maybe 12. And progress report. Oh, by the way, I won't be going to Hungary anymore. The trip is canceled. So I can judge with Dr. Patel, not by, judge with. Okay? And I don't need to do video lecture anymore for the spring. But I still need to do be the judge for the competition. Okay, so these 2 weeks I will use the video. So how much point? So I need 1.5. So let me do the 20. Let me do 27 here. So I give you 0.5 points extra. Okay, so that's the update of the story. I think it's reasonable. Now, today, we are moving on to a new topic. It's about fatigue, okay? So if you go to the online lecture, you can find a part where I mentioned dynamic loading, or so-called the fluctuating loading. So basically, something is carrying a load, but the amount of the load change with time. So in the past, before today, we talk about something carrying some loads, but the amount of the load doesn't change with time. So in that kind of loading condition, we don't worry about fatigue. But for dynamic loading, there's an issue. and because the strength of the material gets weakened when it's carrying dynamic loads. So let me move on to my presentation slide. Okay, so there's something probably you have never learned about in the past, but this idea, this concept is very important for this course. It's highly related to fatigue. It's a kind of measurement or material property called endurance limit. Okay, so what is endurance limit? So basically there's from the Society of Testing and Materials. So endurance limit is also called the strength for fatigue. And there's a definition right there, very important. The value of stress or value of strength at which failure occurs after certain amount of cycles. So if some material didn't carry any cyclic load, so if I apply this force for the first time, so the cycle is like, number of cycles is like 1. So if I do this, then it's not dynamic loading, it's static. The load doesn't change with time. In that case, the strength of this material basically is the same as its original property. But if I start to apply dynamic loads, so the amount of load change with time. If I keep on doing this, I don't know for how many times, 1 million times or 10 million times later, some part of this component somewhere will become weaker if I keep on doing this. Okay? But because strength is in the unit of pressure and also in the unit of stress. That's why the expression, the description right here is value of stress. Okay, and a failure occurs after a certain amount of cycles. So if I keep on doing this dynamic loads 10 million times, and it failed. So that amount of stress, if I apply same amount of stress 10 million times, and right at the 10 million cycle, it failed, somewhere it failed. Then the strength for that failure, you can say it's the endurance limit of that part. And you can say it's the strength, the fatigue strength. Because this material can carry that amount of force for 10 million times. If one day I in lot of cycles, such as 10,000, then you probably can choose an endurance limit with a larger value. But if you are like, for example, for our elevator, it moves up and down every day and probably every minute during the day. So if you are designing for the metal wire, actually our book talk about the metal wire. If you're designing for this, think about the metal wire that carries the elevator. How many people can stay in the elevator? Maybe 10. So probably including the elevator itself, totally it's 2 tons of weight. Could be, right? 2 tons of weight. Like myself, it's 100 kilograms. Patel, probably same amount or even higher, right? So if there are only 6 of us is already counting as probably 8 people. So, the elevator, the metal wire cables are carrying 2 tons of weight. And think about, there's usually a pulley on the top. So, the cable moves up and down. The cable is being bent and released to its original shape, and then bend it, on shape, bend it, on shape, all the time. Every minute, the cable is carrying the loads dynamically. So of course, it will have fatigue issue. So usually, the elevator has a counter in the system. It counts how many cycles it moves up and down. And there's safety guidelines mentioning how many cycles, after how many cycles, you need to replace the cable due to fatigue reason. And we are designing for a certain amount of cycles. If you didn't choose the right amount of endurance limit, or you choose wrong amount of safety factor, it could break early, or you may be designing for too strong cables. Then your company will lose money. Because everything that is too strong basically is a waste of money. Okay, so the idea of Goodman decide to reduce the upper limit for amplitude part of stress. So he believes if you are designing for something, and you are talking about fatigue, then the amplitude part is where you are carrying you have the risk of fatigue. So we shouldn't use yielding strength as our limit, because after a million cycles, the strength already drops. Okay, so that's what he believes. And for the mean value part, if you take a look at the dynamic loads, and if you take a look at the mean value, let's say the mean value is here. In fact, the structure is not always carrying the mean value all the time. Sometimes, of course, it's larger, but for many times it's lower. So the idea is that maybe the mean value doesn't need to use the yielding strength as the upper limit. Maybe we can be a little bit more aggressive. As long as the mean value is not larger than the ultimate tensile strength, then probably we're okay. So this is a very aggressive idea, okay, for the mean value part. When there's mean value and zero amplitude, as long as it's not over the ultimate tensile strength, then choose this point as the design limit. So the original Goodman model decided to become more conservative by reducing the upper limit from yielding strength to endurance limit. So it's a drop. This move is more conservative. However, he enlarged the mean value part because he believes in dynamic loading, you are not carrying this mean value of loads all the time. So he decided to enlarge the horizontal limit to ultimate tensile strength. Usually it's greater than yielding strength, right? That's why you have a new blue curve. That's the Goodman model. So compared to the yield line, what you need to do is basically is to replace the bottom part of the same equation. That's how easy it is, okay? And if you apply safety factor, basically apply n in the right-hand side lower part, then you have this blue dashed model. And in fact, there is so-called a modified Goodman. So what is modified Goodman? Here is the amplitude part, here's the mean value part, and here is yielding strength, ultimate tensile stress, ultimate tensile strength, and endurance limit. Okay, so this is yield line, and this one is Goodman. Okay, but which one is modified Goodman? So modified Goodman is the combination of both. Be conservative, like how Goodman mentioned for the dynamic part. But when you are closer to the when you are closer to static loading, when the dynamic part is low but the mean value part is large, do not use the Goodman, use the yield line. So with the combination of two curves, two lines, this is so-called a modified Goodman. Okay? So how do you design for using modified Goodman? Basically, when you have a design point, you need to check whether you are over the Goodman and also whether you are over the yield part. So if you are within both the original Goodman and the yield line, then you satisfy modified Goodman. Okay, so modified Goodman is a combination of both models. Okay, there's a third model. Third model basically is the most conservative one. Since you sometimes decided to go with the Goodman, sometimes you want to go with the yield line, why not just truly combine both of them? So Soderberg decided to draw a green line right here, connecting the endurance limit and the yielding strength to form a smallest triangular design space. So let's just be very conservative. For the dynamic part, let's do not get over endurance limit. And for the mean value part, let's not be larger than the yielding. So that's why you have a green line right there, the Soderberg model. And the equation basically is to change this part, the mean value part, to the yielding. Then you're done. So basically, three different lines with three different equations. So later on, we will be studying for, again, shaft problems. But I will start to talk about how the shaft could be rotating. So somewhere inside the shaft is carrying dynamic loads. And let's take a look for that scenario based on three different models. And you will see three different levels of safety. Depends on the conservativeness of the model. You will have different amount of safety level. Here's the overall analysis. But you need to be aware of something. have we talked about shear stress in the previous models? There is no shear stress. But how is it possible that we are not considering shearing stress? So what if we have a design that has both normal stress and shearing stress? Do we just ignore the shearing stress? No, it's impossible to ignore any of the loading conditions. Then how is the model not good enough? Okay, so the situation is that you can use von Mises stress. Because from the last time when we talk about distortion energy model, we mentioned the von Mises stress is a kind of equivalent stress. It covers all the loading conditions, including normal stresses and shearing stresses. Okay. So when we apply any stress values to the upper part of the equations, we actually apply von Mises stress. So those values will be including the shearing condition for the material. So in our in our course, in our lecture, we can only handle plane stress or plane strain problems. So here is a force diagram for plane stress or plane strain problem. Again, in all my slides, this should be clockwise, not counterclockwise. So thanks to one of the students who reminded me. So anyway, but it's the same result. So for a general problem like a plane stress or plane strain problem like this, if you try to formulate the von Mises stress, you end up with an equation like this. This is what we had in general, including stresses in the third coordinate, z coordinate. But since we are dealing with plane stress or plane strain, so as z equals to 0, that's why for planar problems, von Mises stress is basically in this form. Okay? It's general, it's not only for shaft, it's for planar problems. So basically we can apply these into our model. So, but where is the mean and amplitude? What do you mean by mean and amplitude? So basically, this could be just one moment for the material carrying certain amount of load. Maybe a second later, some part of the normal stress or shear stress changes. So when you study the Mohr circle, it's like the Mohr circle is changing its size in time. Can you imagine this? So if you are applying dynamic loads to a part, and if you try to study the Mohr circle of some part of the material, then at a certain moment, the Mohr circle looks like this. And when I release, the loads become smaller, so the Mohr circle reduces its size. But if I keep on doing this, the Mohr circle is like this, changing its shape, right? So if you study the principal stresses, maximum shearing stress, they are changing their values with time. So the way you can use the model is like this. You can also study the mean values of principal stresses and also the amplitude part of the principal stresses. Apply to von Mises stress. So you could have mean value of von Mises stress and also amplitude of von Mises stress. Then you can apply the mean part to here, the amplitude part to here. Okay, we will have more examples later on. This is what's going on. So, in general, we are using 3 different fatigue models, and For the upper part, you have mean stress and the amplitude stress. So you will be applying von Mises stresses. But how do we get von Mises stresses? How do we get the mean part and amplitude part of the von Mises stresses? You basically can do this. Okay? This is one way. You can just apply the mean values to the general equation to get the mean von Mises stress, and you can apply the amplitude part to get the amplitude part of von Mises stress. Okay? But how do you get the mean of principal stresses and the amplitude of principal stresses? You can try this. You can apply the mean normal stress and shear stress to get the mean of principal stress. You can apply the amplitude of normal stress, amplitude of the shear stress to get the amplitude of principal stress. And this is the first principal stress. This is the second principal stress. Okay? I should say 1 and 2, not x and y. Basically, they are first and second principal stresses, not the x and y. Typo, sorry. Okay? What do I have later on? Stress concentration. Okay, so let's take a break. If you have difficulty understanding what I have said, you can come here, or let's just take a short break. Okay? See you 10 minutes later. Oh, sorry. Okay, so let's continue on a new concept. So this new concept probably is also a new concept for you, and it's affecting fatigue. So this is the first time we talk about this idea, so-called stress concentration. So what's going on? Well, why do we care about stress concentration? So what's happening is, when you have a structure, let's take a look at a shaft. Okay, that's a shaft. And if I'm applying bending moment, okay? So I do have small diameter here and a large diameter here. And if this is the moment I apply. So what will be the stress in each area? Based on what we have learned, the normal stress would be 32N over pi diameter cube, right? So which part will carry more loads? Which part? This part or this part? Are you guys dead? Do you guys care? Someone is still watching his phone? Do you understand English? So it's very easy. Which part is carrying more loads? Based on this equation. If I want this to be larger, this should be greater. Just tell me. Smaller. Right? If this is smaller, then get greater stress. So here is greater stress over here. Left or right? That guy still don't care. That guy doesn't care. You guys don't care. Why? It's important. This is an important concept. Which one is larger? I don't care about your score, but when I tell you about important concept, it's an important moment. Okay? Which part carries more loads? Left or right? Left or middle? Everyone?
Left.
Yeah, thank you. Thank you so much. Yes, this part is carrying more loads. So if we want to design for this part, we worry about the area that carries more loads, because that's where the structure can break. So we don't even need to care about this part. Okay? So, is it enough? So based on the equation, the stress would be 32m over pi small d cubed. That would be the stress everywhere. Actually on the border, at the parameter, right? Everywhere on the top and bottom. But how about this area? How about this point? So actually, the concept of stress concentration comes into this particular position, because this is the corner point. Okay, and stress actually concentrates at special geometry area. Like if you have a shaft, and here has a small groove. Okay, and if you try, stress is like transmitting the load. So if you apply force, it's like the force is being transmitted and goes to the other side, right? And you can see right here when I'm drawing those force curves, right here it becomes narrower. So fewer material can carry the same amount of stress. So at the necking area or smaller area, they have greater stress. Okay? So same idea, if I'm applying bending, there are tensile forces. So if I try to draw the stress curves, so it's like the stress is being carried like this way. Okay, and it's gonna be like this, and over here there will be some concentrated area. When the stress changes direction, it becomes more concentrated, higher stress right here. Okay, but how do we know how much higher? How much higher? So probably this area carries K times higher of your stress. K times higher of your regular stress. But how much is K? We don't know. Nobody knows. So someone did experiments, already measure the K for you. That's why we have tables. Tables tell you how much times higher the stress will be concentrated at those positions. So if you know, when you have a design, by the traditional equation, you can estimate regular stress, but at some other area, the stress will be K times higher. Do you care about the stress here or the concentrated area? Of course the concentrated area, because the stress at the corner is K times higher. So for all the study we have done, if there is no concept of stress concentration, the stresses that we apply to your homework, to the exam, to your design, we underestimate the stress. There are actually greater amount of stress at the corners. So this is a very important idea. Now, let's take a look at some definition. Stress concentration effect of some location where the stress is greater than the surrounding area. So this is the region. This is the surrounding area. And how do you define it? We use so-called a stress concentration factor. And usually we use this capital K. And the equation is defined as the higher stress over the stress for the reference. So this is the reference stress. So when we are dealing with an area with smaller diameter and larger diameter, we don't care about the large diameter part, because that part carries lower stress. We don't care about here. We use the most critical part as our reference. That's our baseline. But this concept tells us for the stress concentrated area, the stress is going to be even greater than your baseline. How much greater? K times greater. Okay, so here comes a bunch of figures at the back of your textbook, or you can Google it. People has done a lot of experiments to tell you how much K times greater it's gonna be. Okay, so let's now take a look at some scenarios. So this is basically a shaft. If you are dealing with different geometry, this figure doesn't work. This figure only works for this cylindrical shaft, and one part is having a smaller d, the other part is having a greater d, and it's being pulled from the side. Okay, so like pulling like a tensile test. Now it tells you at the corner there is a fillet rounding. Okay, so they did some rounding, and the fillet has a radius of r. The dimension of this r matters. From the diagram later on, you will see how this is affecting the stress concentration factor, basically K times. So over here, let's take a look at the horizontal axis and the vertical one. Basically, the vertical axis is your K, stress concentration factor, K times of your reference stress. The horizontal one is a ratio. It's a dimensionless ratio. It's a ratio between small r, basically the radius here, and small d, the reference diameter. So the ratio is important. Okay? So, which is good, because in the future, if you are designing for a larger shaft, you only care about the ratio, not the diameter itself. So it's a dimensionless way to analyze this. So if you have 0.1, that means the radius is 10% of your diameter. Okay? So it's quite usual radius you will use for rounding, for the fillet, right? You can have even smaller ones. Of course, you can have large ones, but usually you don't have super small. Usually you don't have too large of radius for the fillet, because what do you usually do when you have a shaft like this? You use a lathe, like Teltron. You use lathe to cut. You use a lathe to cut, and in the past we always try to have this 90-degree corner, right, to show a very clean corner, because it looks beautiful if it's like 90-degree cut by the lathe. But actually, it's not a safe design if you have this 90-degree straight corner. Because if you have 0 radius at the corner, that means you are right here at the drawing. What will be your K? Super large, could be 5 times. So when this kind of geometry carries some load, that corner will carry maybe 3 times or 4 times of stress compared to the reference part. I remember when I was a student, I was producing a part in the machine shop. So I was, at the time, I didn't know about this idea. So every time when I use the lathe, I try to make this corner so perfect, 90 degree. I think it's beautiful. I don't like the rounding. And the task was to produce some thread, 公螺牙, produce some thread for the small part. But when I operate the machine, I accidentally use the machine has some collision. So some tool collide with the thinner part. What happened was the entire shaft bended. But the way it bended was like this. It bended like this. So it actually bended at the corner. So that was the first time I experienced bending for this kind of part, right? But at the time I didn't know this is happening mainly because stress concentrate at that point. Because I didn't, 融会贯通 all the courses in one knowledge. I didn't know stress concentration is related to the real part. So I hope you will now learn, okay, those roundings are important because it affects how many times of stress is being applied to the corner. Okay? Now, let's say you have 0.1. So the radius of the fillet is 10% of your small diameter, so you basically here. What affects the stress concentration? The next factor will be the ratio between capital D and small d. So the ratio between this bigger part and the thinner part. So the larger, the worse. So if you have this diameter 2 times of your small part, then you are on this red curve right here. And you can see from 10% of radius coming up to here. So you carry 2 times of load for stress concentration. K equals to 2. Okay, so from now on, when you do mechanical design, do not design a shaft with a lot of diameter change. Now you know. Because from this lecture is telling you it's not good for your part. Your shaft will be weak. The stress will be 2 times larger. If you the stress will be 2 times larger if you have dramatic diameter change. Okay, so try not to change the diameter of the shaft too much. So, if you have, for example, I believe the lowest curve, this is like 1.01, so almost the same, almost same small d and large d. So take a look at how much K you may have. Only like a 1.2 times. 1.2 times larger. So it's much, much better if you can have similar diameter. But of course, in some cases, you may need those for a certain reason. But try not to have too large. If it's a huge change in diameter, then try not to carry too much loads. Okay? And think about the factor of stress concentration. So this is the loading condition for tensile. How about a different situation where you have bending? And if we read the values for 2 scenarios, let's say if we are both reading 0.1 and 2 times of diameter difference. So 0.1, 2 times probably here. And the value goes to 1.75. So for tensile, it's having a value of 2 times. K equals to 2, but for bending, it's 1.7 something. So from here, you can tell the stress concentration behave differently for different load conditions. But I am not expert in solid mechanics. I don't do research on solid mechanics. I don't try to find the main reason why this is happening. The textbook is for undergraduate. It doesn't tell you why. In the future, for graduate study, if you are in the field of solid mechanics or in material division, maybe you can go figure out why bending and tensile provides different amount of stress concentration. So I think in the future, if you're curious, probably you can figure out on your own. I personally didn't figure out. Let's take a look at twisting. So twisting, if I use the same value, different ratio for the rounding, and 2 times of your diameter change, then you have stress concentration of 1.5, around 1.5 times, 1.45, so even lower. So it seems like for a design like this, tensile provides greater stress concentration, bending the second, twisting the third. If we only focus on stress concentration factor, how much times higher of your stress it could be compared to the reference stress. Okay? So I gave some examples at the bottom. You can just take a look at the slide. But let's now know this is a new idea, new concept. And later on, there are 2 more stress concentration factors. Over here, I need to tell you, I tend to put these 2 drawings together and this one on the right and use different colors because they are treated differently later on. Think about tensile and bending. The stress that the material is carrying is normal stress. But for twisting, the material is actually carrying shearing stress. So to be different, for normal stresses, we use KT as the symbol for stress concentration factor of normal stresses. And when we are dealing with shearing stresses, we put an S next to the K. S represents shearing. Why do we do that? Because later on, when we apply to our design equations inside von Mises stress, we do have normal stresses and shearing stresses. So if we have normal stresses, we study for the normal stress concentration factor. For shearing, we look for the shearing stress concentration factor. Okay? We treat them separately. Now, that was static loading condition. But today we are talking about fatigue. So there is a way to estimate the stress concentration factor for fatigue. The way we estimate it is to use another new idea, so-called the notch sensitivity. Q, notch sensitivity. So what is a notch? If you have a geometry on this, and then you have a small geometrical change, it's like a check-on. It's like a notch. So the idea of notch sensitivity is that we want to see how stress concentration factor, how sensitive stress concentration factor is when you are applying the load dynamically. Okay, but if you try to understand it in a description, sometimes it's hard to understand. Let's try to understand it with the mathematical equation. So if Q equals to 1, in that case, so Q is a value from 0 to 1. If Q equals to 1, F represents the dynamic loading. So Fs means dynamic loading and shearing. So if Q equals to 1, you will see Kf equals to Kt. So if there is a scenario when Q equals to 1, the stress concentration factor in dynamic equals to the 1 in static. Okay? But in reality, Q is not 1. Okay, so later on the table will tell you, oh, Q is not 1, Q is 0 point something. So Q is, in this figure, you can see, oh, there are some scenario Q equals to 0.8. So when you apply to here, if Q is not 1, Q is 0.8, that means Kf is slightly smaller than Kt. So what you studied in the previous page, that was for static loading. And for certain material condition and low condition, a geometrical condition, the dynamic stress concentration is slightly lower than the static stress concentration. And how much lower? Defined by this table Q. And I will tell you how to determine Q. But you need to know, for a material carrying, with certain geometry, carrying certain loads, the stress concentration behavior is different when it's under static load or in dynamic load. And the difference can be determined by this equation. Okay? Now, similarly, you apply the same equation for the shearing. So let's take a look at the diagram, the figures right here. On the left is the notch sensitivity for normal stresses. On the right is notch sensitivity for shearing stresses. So let's take a look at normal stresses first. So if you take a look at the horizontal axis, it's basically the radius. Okay? So this table works when you have small geometrical change within 4 millimeters. So if it's larger than 4 millimeter, then it's almost concentrated and close to 1. So if you have geometrical change that is larger than 4 millimeter, it won't be considered as a notch. So you just treat it. It won't affect too much. The stress concentration factor is almost the same. But when you have small geometry, like right here you have this rounding, fillet radius. If the radius is on like 1 millimeter, then for the stress concentration, it behaves differently in static load and the dynamic load. Now, so let's say our notch radius is 1 millimeter. So let's take a look at the curves and see how the curve changes. The curve changes with ultimate tensile strength. So basically, material strength. If you have larger value, that means you have stronger material. When the material is stronger, then the difference between Kt and Kf is not so much, because Q is close to 1. So Kt is almost equals to Kf. So in the future, when you are designing for very hard material, strong material, and you worry about stress concentration, you probably don't need to worry about two scenarios, dynamic or static. Because they may have the similar stress concentration behavior because Q is close to 1. But if you are dealing with soft materials, like when this is steel, if you have lower ultimate tensile strength, or like aluminum alloy compared to steel is softer, then a softer material tend to behave differently when it's carrying static or dynamic loads. But the Q is not close to 1. Q could be as low as 0.5. Okay? Similarly, this is for the notch sensitivity, the equation for you to calculate stress concentration for shearing. Okay? And basically, these are the drawings. So how do I memorize those? Usually when I studied this, I decided to have a table like this to remind myself. Okay, if you're carrying static load and normal stress, then you use KT. So go back to the textbook and find, okay, this is for KT. Then I'm studying for the right number. And if you are having static load but shearing stress, then KTS. So S for shearing. So this is for static. But if you want to study for the stress concentration in the low dynamic loads, you need notch sensitivity. You need Q and QS. So you determine the static one first, use Q to determine the dynamic ones. Okay, so this is how I memorize the sequence of calculating for K. And we may have 4 different Ks, 4 different K values. If we apply those to our design equations, where are they? So this is what we had, but if you look at here, this is the principal stress, first and the second. And this is for shaft only. If we dig in and try to figure out, we realize you may have normal stress here and shearing stress here. So if the material is truly behaving differently for normal stress and shearing stress, and we truly want to apply a more appropriate K, what you can do is the true stress at the corner probably is KT times of your normal stress. And at the corner, you have KTS times of your shearing stress. So this is how you can apply stress concentration factor. Charge the force. Definitely, I don't need the same amount of the cycle. The cycle that requires to break it probably smaller because I apply a stronger force. So from here you can see the decrement of strength depends on how you apply the load dynamically. Okay? So later on when we study fatigue, the force applied to the structure is very related to the so-called fatigue strength. Okay, so here is some examples. So you can take a look at the horizontal axis and the vertical axis. The horizontal one is in a logarithm scale. So here is like a very small amount of cycles, but over here, this is already 1 million cycles. Okay, and if you look at steel, originally, when the cycle amount is small, 1,000 is considered as small amount of cycles. or 10,000. They didn't even measure the strength before 10,000. And they start the experiments to study the strength of steel, and they realize the strength decreases when you apply more amounts of more cycles of loads. But this drops to a certain point, it starts to saturate. It doesn't drop anymore. That's for steel. But different material may have different behavior. Aluminum is a softer material compared to steel. It tends to saturate a little bit, but still keep on dropping. Okay, so softer material tend to be weakened and weakened if you apply more cycles of loads. However, there's usually somewhere after a certain amount of cycles of loading, the strength kind of saturate. Okay, so we usually call this corner point the endurance limit, but this amount has some other relationship with the amount of cycles and also the applied force. So when you see a figure like this, and you see a corner point right here, and it reads as 1 million cycles of loads, and 30 for this one KSI stress, in stress. So what does it mean? It means steel will fail after carrying a dynamic load in the amplitude of 30 KSI for 1 million cycles. So this figure basically tells about this relationship. Okay, so if you apply a greater amount of stress, for example 40, if you keep on applying 40 KSI of stress dynamically, then for how many cycles this material will fail? Basically, you read it from here and goes down here. Okay, around 5 times of 10 to the power of 4, so 50,000 tons. So does that match what I said? If you apply a greater stress, the material can only carry a lower amount of cycle. And this curve basically describes how many cycles it can carry. And if you apply a lower stress, lower than endurance limit, then you will see this, for example, 20 KSI, and it doesn't even touch the curve. That means if you apply 20 KSI, the material can stay strong for a very long amount of cycles. Okay, so then your design will be very safe. Okay, so it's good to know that the material has this corner point, because any force that is lower than this endurance limit doesn't cause fatigue issues too much. Okay? Now, when we study so-called fatigue analysis, we need to know about the loading condition. So when we talk about the dynamic loads, it's unusual that you have dynamic loads with same amplitude all the time. Usually it's very random. So for us as an engineer, when we want to design for want to design for fatigue due to fluctuating loads. It's difficult for us because we sometimes is large, sometimes is even larger, sometimes it's not so large. So the most conservative way to do this design is to find the average. So use that average as a base point, base level, and then find the largest amplitude. We call this area like in different textbook, they use different terms. Sometimes people call this the range of the stress. So some book will say if this is mean, or some will just use average, right? So if they use mean, they sometimes use the n for the to represent mean value, and for average, sometimes they use a to represent average, or they use avg to represent average. They are the same thing. And for the amplitude, I saw some book called this range. So they use R to represent so-called the range. Or I have seen they use amplitude here. So they have an A right here. And what's confusing is some book use average, some book use amplitude. Both starts with A. But in my case, I chose to follow one book, which is using mean and amplitude. So I am using this one and this one. If you are checking some other book, it could be average and range. Okay? But they are the same thing. So why didn't we figure out the average of the amplitude? Because it's troublesome. So to be safer, they just pick up the largest one, just in case you have a dynamic load in this amount of amplitude. Okay? So after knowing the stress could be applying with a mean value plus or minus the amount of amplitude, then how do we deal with how do we deal with this? So there is a very basic idea. There is a basic idea. So the idea one is, how about a situation where we have zero mean value, but some amplitude? What kind of situation is that? For example, for this microphone, if I'm bending the microphone both ways constantly, if I'm doing this. So for, let's say, the upper part of this shaft, when I bend down, it's being pulled, and if I bend up, it's being compressed. So this part of the material is experiencing tensile compression. But if I am applying same amount of bending moment all the time, then the mean value of this stress would be zero. So for the first scenario, if you study, if this is time, if this is stress, you will see something like a sine curve. So the mean value is zero. And you have same amount of the amplitude. Same amount. Okay? So in this particular case, it's interesting that when you see zero mean of the stress, you might think, okay, it's not too serious. However, you could have large amplitude if you apply great amount of bending moment. So in that situation, the simplest idea is that, let's say the amplitude cannot be larger than the yielding strength. Then we should be fine, right? The simplest idea is like that. So we start to make a new diagram. This is a new way to study for the stress due to under the situation of fatigue. So basically designed for fatigue. So when we do this, how do we design the horizontal axis and the vertical? We chose to study the mean value of the stress in the horizontal axis and the amplitude part of the stress in the vertical axis. And if you look at the first idea, it seems like we have zero mean right here, and we have some amount of amplitude along the vertical axis. So if I want to put a dot in this diagram, basically the design right now is somewhere on this axis. So we want that point to be within the yielding. That's the easiest concept, because even for both bending up or bending down, you don't want the stress inside the material to be greater than yielding. That's why we have the first concept. Secondly, on the very opposite scenario is where you have non-zero mean, but zero amplitude. So what is that? That is basically static. If there's no amplitude, then I am applying a constant force applied to the material, and it doesn't change with time. That's basically the second scenario. In that case, what's the usual model? Basically, the stress, again, needs to be smaller than or equals to the yielding strength. That's why on this horizontal axis, if we have non-zero mean value of the stress, but zero amplitude, that means our design point is on the horizontal axis, and we want that point to be within the yielding strength. So if I try to satisfy both scenarios, one idea is to draw this red line right here, and this red line basically is valid for both scenarios, for both extreme scenarios. So how about the design somewhere in the middle? That means I may have a loading condition with certain amount of mean value and also certain amount of amplitude. So by this curve, we realize we have a limit. That design cannot be on the upper right corner of this red line. The worst would be staying on the red line. If you can stay on the left lower corner, that would be better. Okay, so that would be the first model we use, so-called the yield line. So basically all the idea came from the limit due to yielding. So we draw this yield line, and later on, when we compare with different models, we try to formulate this equation in a certain form, and also we try to apply safety factor. So just like what we have learned in the past, whenever we have a limit on the right-hand side of the equation, basically this is the equation, the red line is this one, okay? And whenever we want to apply safety factor, we apply at the bottom of the right-hand side, right? We apply a value that is larger than 1. So when we do that, we have a smaller design space. Originally, we have a triangular design space within this red line. After applying safety factor, our design space becomes smaller, which means we can only allow our design to stay in here. So we are having a safe gap from the yielding. That's why we apply safety factor. Okay? So mathematically very simple. And right here is just what I have said. We would like to divide the left-hand side by yielding strength to have this format. Because later on in the following 2 models, we use equations in this form. So later at the end, we will have comparison of all 3 models. Okay? So it should be very simple. Now, there is a new model. It's called the Goodman. What happened to Goodman? So the situation is this. When we study so-called amplitude part of stress, it's basically the dynamic part. That's where the material is carrying cyclic stress or dynamic stress. So Goodman has an idea. Maybe the amplitude part cannot be greater than endurance limit. Because maybe when this material is very fresh, very new, it's strong, but after certain amount of cycles, after certain cycles of loads, the strength of the material drops. So at the beginning, maybe the material can carry this amplitude part of the stress, but later on it cannot. So in Goodman's idea, maybe the amplitude part cannot be larger than your endurance limit. But how do you define your endurance limit? It depends on how many cycles you are focusing on. So if you are only designing for low amount, because without the K, everything is stress analysis without considering stress concentration. So how do we consider them? Basically, apply a proper K times of stress to the right place. And I suggest for the normal stress, you apply KT, and for the shear stress, apply KTS. Is this the only way to apply stress concentration? I have to tell you no. Because I have read different textbooks, different homework examples, exercises. I noticed sometimes they just apply K here or somewhere. So what does that mean? That means there's no right answer. There's no exact answer. Okay, and think about why this is happening. All these K values were determined by experiments. What you have seen right here, they are estimations from experiments. Otherwise, how did they get that? They must have done some experiments to have multiple points, maybe some research done 30 years ago, and then they draw a curve to provide something for the textbook, to provide some professors to tell you this kind of phenomenon. And today, we are using it. We don't use it like this is the only true value. Any value on the curve is just an estimation based on a bunch of experiments. And maybe one day, you're not dealing with steel, you're dealing with a new material. And you want to say, hey, let's try to make a guess. What would be the level on this field? You may not know. Because this is result based on certain experiments. Okay, but after learning this course, it helps you to understand the equation you have learned in the past is not the same as the reality. The reality is there will be stress concentration. And this is one way to estimate. I think in this course, we did a lot of estimation. So what would be the best way to determine the stress? Do experiments. And do a lot of experiments. That, of course, is the best way. But it's the most expensive way and most time-consuming. So at least, maybe you can apply enough theory and mathematics to have good estimations. So you have certain kind of theoretical results with certain knowledge you know. So you make less mistakes. Then you probably produce your product, do your experiments. The result won't be too far away from your estimation. Okay, so like I said, I have seen textbook apply K in front of each stress, and I have seen K being applied directly in front of the principal stress. They can just treat the principal stress as a normal stress. It is. And just apply KT right here. But mathematically, if you truly compare this way and directly apply KT to here, they will be two different values. So one will be larger, the other one will be smaller. If you treat your stress larger, that means you are aware of greater stress. So you are more conservative. So it really depends on how conservative you are. Okay? Here's for fatigue. These are the three fatigue models with von Mises stresses in the case of mean value part and the amplitude value part. And I told you those can be determined by the general equation in terms of principal stresses, and they can also have mean value part and amplitude part. And for all the principal stresses, you have equations from Mohr circle. Now you will see there could be different ways of applying K's. So let's take a look. When we are talking about mean value part of principal stresses, inside the mean value part, you have mean value of normal stress. Of course, mean value is like a static force. So you can treat it as a static normal stress. That's why we apply KT. Normal force, static. But for the tau, the shearing stress, for the mean value part, it's a mean stress. So it's a mean value, static value, doesn't change with time, but in the shearing. So the K I'm using is TS, KTS, for the shearing, static. For the amplitude part, we will be using the amplitude part of the stress and the amplitude part for the shearing stress. So they are treated as the dynamic ones. So if we treat those stress values as dynamic stress values, when we apply stress concentration, we can apply the dynamic ones. So this is basically normal stress in the amplitude part, so normal, dynamic. Normal stress, dynamic, so I'm using KF. This one, shear stress, dynamic, so I'm using KFS. So from here you can see there are 4 different Ks. There could be 4 different Ks. And each of them could have different values if you check on the tables that I showed you. Okay? So up to here, this probably is the most complicated equation. If you apply everything to here, this equation will be super large, right? Because all the von Mises stress can be determined by the square root, and each term right here can be determined by these. And think about the sigmas. Sigmas can be determined by this 32 m over pi d cubed. So if you start from the bottom and then try to build the complete equation, it's super large. Okay? So I try not to put them all together. And I never ask a student to memorize it. It's too large. But every equation that I'm showing you has some kind of concept. Each concept is tightly connected with each other. I don't want you to miss any concept. So I think today's lecture is quite important. I recommend you to re-watch the video or review this part by yourself. Because if you can keep in mind of those concepts right now, it will help you for a very long time. That's what I believe. That's why I want you to pay attention earlier. Okay, if you already pay tuition and sit here, and I'm telling you this is definitely new. I don't believe any other lecture will teach you this. That's why I hope this lecture you will pay attention. Maybe later on when I solve math equations, that's the lecture you can just fall asleep. I don't mind. Because that's just solving problem and your score. But here, I think concept-wise is important. You can truly learn something. Okay, that's it for today. And it's already 12 o'clock. So I will stop right here. Tomorrow we will solve a problem. And based on the schedule, I need to give you a problem tomorrow. Okay, so basically it's gonna be something similar to those homeworks, but asking you to consider stress concentration and fatigue. Basically, something like that tomorrow. Okay, thank you, bye-bye.